January 19th, 1945, 1423 hours, Beneed Airfield, Germany. Test pilot Heini Dittmar strapped himself into the cockpit of the most radical aircraft ever conceived, a flying wing with no tail, no fuselage, and swept wings angled at 60 degrees. The Horten 229, designated V3, represented everything conventional aeronautics said was impossible. German High Command had rejected the concept twice. The Luftwaffe's Technical Bureau had called it aerodynamically unstable and operationally unsuitable. One senior official had famously dismissed the design as a flying boomerang that will kill its pilots before it kills any enemies. Dittmar advanced the throttles of two Junkers Jumo 004B turbojet engines, each producing 1,962 pounds of thrust. The aircraft began rolling, accelerating with startling speed. At 180 kilometers per hour, the nose lifted. At 220, the main gear left the runway. The Horten brothers' impossible dream was airborne. What happened over the next 12 minutes would remain classified for 40 years. The aircraft reached 590 miles per hour, faster than any propeller aircraft could achieve. It climbed to 49,000 feet, higher than any Allied fighter could reach. Its radar signature, measured by ground stations, was barely detectable, a ghost on German radar screens designed to track Allied bombers. Dittmar landed with hands trembling, not from fear, but from understanding what he'd just experienced. He told the Horten brothers waiting at the runway's edge, "You've built the future. The question is whether anyone will understand it before the war ends." They didn't. The Horten H229 program was canceled 6 weeks later. The prototype was captured by American forces. The revolutionary design was dismissed as a Nazi curiosity, locked in warehouses and forgotten for decades. The technology that would have given Germany air superiority in 1945 was abandoned as a failed experiment. 60 years later, that same rejected design became the foundation for the B-2 stealth bomber, the most advanced aircraft in human history. The swept wing configuration, the flying wing layout, the radar-evading shape, all traced directly to a, quote, dangerous German prototype that bureaucrats had rejected as impossible. This is the story of how rejected genius became revolutionary technology, how wartime desperation produced peacetime innovation, and how the future of flight was invented by two brothers working in a glider club who understood aerodynamics better than the engineers who dismissed them. The Horten brothers, Walter and Reimar, began building flying wings in 1931, not from military ambition, but from pure fascination with flight efficiency. They operated from a glider club in Bonn, Germany, with no formal engineering education, no institutional support, and no budget beyond what they could scrape together from odd jobs. What they possessed was intuitive understanding of aerodynamics that formal training often suppresses. Conventional aircraft design in the 1930s followed established principles: fuselage for crew and cargo, wings for lift, tail surfaces for stability and control. This configuration worked, but it was inefficient. The fuselage produced drag without generating lift. The tail surfaces created additional drag while adding weight. The entire structure was a compromise between stability and performance. Walter Horten, the elder brother at 22 years old in 1931, asked a question that trained engineers considered naive. Why not eliminate everything that doesn't produce lift? Build an aircraft that was all wing, with crew, engines, and control surfaces integrated into a single lifting surface. Eliminate parasitic drag entirely. Create pure aerodynamic efficiency. The answer from conventional aerodynamics was immediate: impossible. Flying wings were inherently unstable. Without a tail, the aircraft would pitch and yaw uncontrollably. Without a fuselage, there was no moment arm for control surfaces to act upon. The design violated fundamental principles of aircraft stability that had been established since the Wright brothers. The Horton brothers didn't argue, they built. Their first flying wing glider, the Horton I, flew in 1933. It was small, crude, made from wood and fabric, and controlled through wing-mounted elevons, combined elevator and aileron surfaces that provided pitch and roll control simultaneously. The aircraft was marginally stable at best, requiring constant pilot input to maintain level flight, but it flew, and it demonstrated efficiency that conventional gliders couldn't match. The H-2 followed in 1934, incorporating lessons learned from the first prototype: better stability through refined wing twist, improved control response through larger elevon surfaces. The glider competed in national soaring competitions, outperforming conventional designs with pilots who understood its handling characteristics. By 1936, the Horton brothers had built 5 flying wing gliders, each more refined than the last. Their designs attracted attention from the Reich Luftwaffe Ministerium, the German Air Ministry, but the response was dismissive. Oberst Ernst Uttert, head of the technical office, reviewed their designs and concluded, quote, "Interesting theoretical exercise, no practical military application. Continue as civilian research if desired." This rejection would prove catastrophic for Germany and transformative for aviation history. Had the Luftwaffe invested in flying wing development in 1936, jet-powered versions might have been operational by 1943. Instead, the technology languished until desperation forced reconsideration. The transformation began in 1943 when Hermann Göring issued a requirement for an aircraft capable of carrying 1,000 kilograms of bombs at 1,000 kilometers per hour over a range of 1,000 kilometers, the 3x1,000 specification. No conventional aircraft design could meet these requirements. The speed demanded jet propulsion. The range demanded efficiency no existing design could achieve. The combination seemed impossible. The Horton brothers submitted their proposal, a jet-powered flying wing. The design eliminated drag that limited conventional jets' range. The integrated structure reduced weight. The swept wings delayed compressibility effects that plagued early jets at high speed. On paper, the HO-229 met Göring's requirements when no other design came close. The initial response was skeptical. General Major Adolf Galland, commanding German fighter forces, reviewed the proposal and expressed doubt. These brothers have built gliders. They have no experience with powered aircraft, no understanding of military requirements, and no proven manufacturing capability. Their design is theoretically interesting, but practically worthless. But Germany's situation was desperate. By late 1943, Allied bombers flew over Germany with near impunity. Conventional fighters couldn't climb fast enough to intercept at altitude. The few jets in development, the Me-262 and He-162, were promising but conventional in layout, limited by the same aerodynamic constraints that plagued propeller aircraft. Göring, desperate for any advantage, authorized the HO-229 program in August 1944. The Horton brothers received their first real funding, access to jet engines, and a mandate to produce an operational fighter bomber. They had 6 months to achieve what conventional aerospace companies had failed to accomplish in years. The technical challenges were immense. No wind tunnel data existed for swept flying wings at transonic speeds. No control system could stabilize an aircraft without conventional tail surfaces at jet velocities. No manufacturing process could produce the compound curves required for the wing's leading edge. Every aspect of the design required innovation. The Horton brothers solved problems through intuition and testing rather than calculation and prediction. They built flying models, flew them, crashed them, analyzed the wreckage, and built better versions. This iterative approach, now standard in modern aerospace development, was considered reckless by German engineering culture that emphasized theoretical analysis before physical testing. The first powered prototype, the HO-229V1, was actually a glider test bed. Flown in March 1944, it validated the basic configuration, stability, and control characteristics at speeds up to 180 miles per hour. The aircraft was docile, responsive, and efficient, contradicting every prediction from conventional aerodynamicists. The V2 prototype, first flown in December 1944, added two Junkers Jumo 004B jet engines buried in the wing roots. This configuration minimized drag while protecting the engines from damage. The inlet design, developed through trial and error, provided adequate airflow at all flight conditions, a problem that had plagued other early jets. Test pilot Erwin Ziller flew the V2 on its maiden flight December 18, 1944, from Oranienburg Airfield. His report captured the aircraft's revolutionary nature. The handling is unlike any aircraft I've flown. There is no sensation of the nose hunting for trim. The aircraft goes where you point it instantly. Speed builds faster than any jet I've tested. I reached 600 kilometers per hour in level flight without exceeding 80% throttle. This is not an airplane. It's something new. The performance specifications, documented in captured German records, defied contemporary aircraft. Maximum speed 977 kilometers per hour at 12,000 meters. Service ceiling 16,000 meters. Range 1,900 kilometers with 1,000 kilogram bomb load. Rate of climb 22 meters per second. Wing loading 230 kilograms per square meter. These figures exceeded the Me-262's performance by 15 to 20% across all parameters, achieved with less powerful engines through pure aerodynamic efficiency. The flying wing's drag coefficient was approximately 0.019, compared to 0.028 for the Me-262. This 32% reduction in drag translated directly into speed, range, and climb performance. But the most revolutionary aspect wasn't intentional. The Horten 229's composite construction, wooden structure with charcoal-impregnated plywood skin, absorbed radar energy rather than reflecting it. The swept leading edges deflected remaining radar returns away from receivers. The buried engines eliminated the massive radar signature of exposed jet intakes and exhausts. The aircraft was, accidentally, the first stealth fighter. German radar operators at Peenemünde documented this phenomenon during early test flights. The Horten 229 appeared on radar screens as a target approximately the size of a small bird, virtually undetectable at combat ranges. The operators assumed their equipment was malfunctioning until visual observation confirmed the aircraft's position. They reported the anomaly to headquarters, but the implications weren't understood until decades later. The program's nemesis was time. By January 1945, Germany was collapsing. The Horten brothers had proven their concept, but lacked resources for production. The Gotha Aircraft Company was assigned to manufacture operational HO-229s, designated GO-229 in production configuration. The first production aircraft, the V3, was 95% complete when American forces captured the factory on April 14, 1945. The capture team, led by Colonel Harold Watson of the Army Air Forces, recognized the aircraft's significance immediately. Watson's report to headquarters stated, "The aircraft recovered at Friedrich Roda represents design concepts 20 years ahead of American development. Recommend immediate transport to the United States for detailed analysis. This may be the most important technical capture of the war." The V3 prototype was shipped to Wright Field, Ohio, where it underwent extensive examination. American engineers documented every aspect of the design: the innovative control system, the structural efficiency, the engine installation, and the mysterious radar-absorbing properties. Their conclusions, classified secret until 1979, revealed both admiration and disbelief. Dr. Theodor von Karman, leading the scientific advisory group analyzing captured German technology, wrote, The Horten flying wing represents a fundamental departure from conventional aircraft design that American aeronautics has not seriously considered. The design achieves performance impossible with traditional configurations while demonstrating stability characteristics we believed theoretically unattainable. The Horten brothers, working without formal engineering education, have advanced aerodynamic understanding beyond our most accomplished researchers. The American response to this captured technology was, paradoxically, rejection. The Army Air Forces commissioned Northrop Aircraft to develop an American flying wing bomber, the XB-35 and later YB-49, but these programs used Northrop's independent designs rather than adapting the Horten configuration. When the YB-49 suffered control problems and a fatal crash in 1948, the Air Force abandoned flying wing bombers entirely. The official conclusion: flying wings were inherently dangerous. The technology was shelved. The Horten research was archived. The future of aviation was postponed by 3 decades. The irony escaped contemporary observers. The Horten design stability came from specific wing twist distributions and center of gravity positioning that Northrop's designers hadn't replicated. The German brothers had solved stability problems through empirical testing that American theoretical approaches failed to reproduce. By dismissing the Horten configuration and developing independent designs, American engineers repeated the same mistakes that had caused skepticism about flying wings since the 1930s. The Horten brothers survived the war. Walter served in the Luftwaffe until capture, was interrogated by American intelligence, and eventually returned to civilian life in Germany. Reymar emigrated to Argentina in 1948, where he continued flying wing research under contract to the Argentine Air Force. Both brothers spent decades watching aviation evolve in directions they had anticipated in the 1930s, frustrated that their insights remained classified and unrecognized. Reymar Horten, in a 1983 interview, expressed this frustration directly. "We solved the flying wing problem in 1943. We demonstrated an aircraft that exceeded every performance parameter of conventional jets. We showed that the configuration was stable, controllable, and practical. The Americans captured our work, studied it, classified it, and then proceeded to make every mistake we had already corrected. 30 years of aviation development was wasted repeating our early failures." The vindication came, eventually, but too late for the Horten brothers to participate. In 1974, DARPA, the Defense Advanced Research Projects Agency, initiated studies into stealth aircraft technology. Researchers examining ways to reduce radar signatures rediscovered the principles the HO-229 had accidentally demonstrated. Swept edges deflect radar. Composite materials absorb it. Buried engines eliminate major reflection sources. The Lockheed Skunk Works, contracted to develop the first purpose-built stealth aircraft, studied every available source on radar signature reduction. Among the documents reviewed were the 1945 reports on captured German aircraft, including detailed radar measurements of the HO-229. The design team, led by Ben Rich, recognized immediately what German radar operators had documented 30 years earlier. The flying wing configuration was inherently stealthy. The F-117 Nighthawk, first flown in 1981, incorporated faceted surfaces to deflect radar, a different approach than the HO-229's curved surfaces, but achieving similar results. The aircraft's angular appearance seemed radically new, but the underlying principles traced directly to wartime German research that American engineers had dismissed and forgotten. The B-2 Spirit, first flown in 1989, went further. Northrop Grumman's design team explicitly referenced the Horten configuration, creating a flying wing with swept leading edges, buried engines, and composite construction, the same features the HO-229 had pioneered 44 years earlier. The B-2's wing sweep angle of 33 degrees, its control surface arrangement, and its engine inlet design all showed clear lineage to the German prototype. Jack Northrop, founder of Northrop Corporation and flying wing advocate since the 1940s, was briefed on the B-2 program shortly before his death in 1981. According to witnesses, the 85-year-old engineer, confined to a wheelchair and unable to speak clearly due to illness, was shown classified drawings and models of the aircraft. He studied them intently, then wrote on a notepad, "Now I know why." The question he answered was one that had haunted him for 30 years. Why had the Air Force canceled his YB-49 flying wing bomber in 1949? The answer, finally revealed through the B-2's existence, was that the technology wasn't ready for the mission. Flying wings offered revolutionary performance, but required control systems beyond 1940's capability. Only with digital fly-by-wire technology, computers making thousands of stability corrections per second, could the configuration achieve its potential. The Horton brothers understood this limitation. Their solution was simpler: design the wing to be inherently stable without active correction. Their specific wing twist distribution, varying from positive incidence at the root to negative incidence at the tips, created natural stability that required no computer assistance. This approach worked at the speeds the HO229 achieved, but became problematic at higher Mach numbers where the B-2 operated. Modern analysis of the HO229 design, conducted using computational fluid dynamics unavailable during the war, confirms the brothers' intuitive solutions were aerodynamically correct. Their wing twist matched optimal distributions that computers would calculate decades later. Their control surface arrangements provided adequate authority at all flight conditions. Their center of gravity positioning maintained stability throughout the flight envelope. The HO229 wasn't just ahead of its time, it was correctly ahead of its time. The brothers solved problems through empirical observation that formal education might have told them were unsolvable. Their lack of theoretical training became an advantage, freeing them to experiment without preconceptions about what was impossible. The stealth characteristics, while accidental, demonstrated a principle that would become fundamental to modern military aviation. Shape matters more than materials for radar signature reduction. The HO229's wooden construction contributed to its low radar signature, but the primary factors were geometric: swept leading edges, smooth blended surfaces, and engine placement that eliminated major reflection sources. Northrop Grumman's engineers, developing the B-2 44 years later, validated this understanding through extensive radar testing. Their analysis, partially declassified in 2009, concluded, the Horton HO229 achieves radar cross-section reduction through passive shaping that we have only recently understood how to optimize. The aircraft's configuration, while designed for aerodynamic efficiency, incidentally produces signature reduction comparable to early dedicated stealth designs. This suggests the brothers Horton possessed intuitive understanding of electromagnetic scattering that formal education in the 1940s could not have provided. The final irony of the Horton 229 story involves the aircraft's intended role versus its ultimate influence. The Horton brothers designed a fighter bomber, an aircraft to destroy enemy targets through speed and surprise. The technology's greatest impact came through reconnaissance and strategic bombing, the B-2's nuclear deterrence mission that relies on stealth to penetrate defended airspace without firing a shot. The same principles that would have allowed the Horton 229 to attack Allied bombers in 1945 now ensure the B-2 can reach any target on Earth without detection. The same swept wing configuration that promised German air superiority now guarantees American strategic dominance. The rejected design became the backbone of the most powerful air force in history. The technical specifications of the B-2 Spirit reveal how thoroughly modern aviation has embraced the Horton brothers' vision. B-2 Spirit, 1989. Wingspan, 172 feet. Length, 69 feet. Empty weight, 158,000 pounds. Maximum speed, 628 miles per hour, high subsonic. Range, 6,900 miles, unrefueled. Service ceiling, 50,000 feet. Radar cross-section, classified, estimated 0.1 meter squared. Unit cost, $737 million, $1997. Horton HO229V3, 1945. Wingspan, 55 feet. Length, 24 feet. Empty weight, 10,140 pounds. Maximum speed, 607 miles per hour. Range, 1,180 miles. Service ceiling, 52,500 feet. Radar cross-section, unknown. Estimated similar to small bird. Unit cost, approximately 500,000 Reichsmarks. The scaling difference is enormous. The B-2 is more than 3 times larger and carries vastly more sophisticated systems, but the fundamental configuration is identical: flying wing, swept leading edges, buried engines, all-wing crew accommodation. The concepts the Horton brothers developed in a German glider club became the foundation for aircraft costing $750 million each. The story extends beyond military aviation. Commercial aircraft designers have increasingly recognized flying wing efficiency advantages. Airbus, Boeing, and emerging manufacturers have all studied flying wing configurations for future airliners. The challenges remain significant: passenger accommodation, emergency egress, certification standards designed around conventional aircraft, but the potential efficiency gains of 20 to 30% over conventional designs make development inevitable. NASA's X-48 blended wing body demonstrator, flown between 2007 and 2013, explored flying wing configurations for commercial transport. The design borrowed explicitly from Horton research, incorporating the same principles of distributed control surfaces and optimized wing twist that the German brothers developed through empirical testing. NASA engineers, reviewing historical documentation for the program, were repeatedly surprised to discover that solutions they developed through sophisticated computer modeling matched those the Hortons achieved through observation and intuition. Dr. Norman Princeton, Boeing's chief technology officer for the X-48 program, acknowledged this heritage in a 2010 interview. "We've spent billions of dollars developing aerodynamic understanding that validates what 2 German brothers figured out in a glider club 80 years ago. The flying wing is more efficient, more capable, and more adaptable than conventional configurations. We just needed 70 years to develop the technology to exploit it safely." The Horton legacy extends to unmanned aircraft as well. Modern drones increasingly adopt flying wing configurations for the same reasons the HO229 demonstrated: efficiency, stealth, and simplicity. The Northrop Grumman X-47B, designed for carrier operations, uses a flying wing layout directly descended from Horton concepts. The Lockheed Martin RQ-170 Sentinel, operated over denied airspace, achieves its stealth characteristics through shape derived from the same principles the HO229 accidentally demonstrated. The transformation from rejected curiosity to foundational technology took 60 years. The Horton brothers, insights dismissed as dangerous and impractical in 1936, became essential by 1996. Their empirical approach, criticized as unscientific, produced solutions that theoretical analysis couldn't achieve. Their vision of pure aerodynamic efficiency, mocked as naive, became the standard by which modern aircraft are judged. Walter Horton died in 1998, having lived to see the B-2 Spirit validate everything he and his brother had designed half a century earlier. In his final interview, conducted by German aviation historian David Mira, Walter reflected on the journey from glider club to stealth bomber. We never imagined military applications when we started. We wanted to build efficient aircraft, pure flying machines without the compromises that conventional designs required. The war gave us resources to develop our ideas, but also destroyed the opportunity to see them realized. For 50 years, I watched aviation repeat our early mistakes, developing flying wings without understanding what made them work. The Americans who captured our aircraft analyzed every component but missed the essential truth. The flying wing works because we designed it as a complete system, not as an adaptation of conventional concepts. You cannot add flying wing characteristics to a traditional airplane. You must begin with the flying wing and only add what's necessary. This is what Northrop failed to understand in the 1940s and what they finally grasped with the B-2. Do I resent that our work was classified, hidden, forgotten? Perhaps, but the ideas survived. The principles we discovered through trial and error became foundations of modern aviation. Our gliders fly in the B-2, in the F-117, in drones that circle above battlefields worldwide. The future we imagined in 1931 arrived eventually. We just weren't there to see it. Reimar Horton died in Argentina in 1994, having spent his final decades designing flying wing agricultural aircraft and light transports. His designs, while never commercially successful, demonstrated that flying wing principles applied to civilian aviation as effectively as military. The aircraft he built in Argentina were elegant, efficient, and stable, vindication of concepts that had been rejected 60 years earlier. The final Horton aircraft, the Horton XV, flew in 1960. It was a two-seat flying wing sailplane, returning to the brothers' origins in glider design. The aircraft achieved glide ratios exceeding 40-1, meaning it could travel 40 feet forward for every foot of altitude lost. This efficiency, impossible with conventional glider designs, demonstrated that the flying wing's advantages scaled from sailplanes to strategic bombers. The XV's pilot, Heinz Scheidhauer, described the experience in terms that echoed test pilots' descriptions of every Horton aircraft. It flies as if the air itself is carrying you. There's no sensation of fighting the airplane, of forcing it to do what you want. You think, and the aircraft responds. This is what flight should feel like. The aerodynamic database accumulated through Horton testing, from the Horton I glider of 1933 to the Horton 229 jet of 1945, represents one of history's most comprehensive empirical investigations of flying wing behavior. This data, captured by American forces and preserved in archives, became foundational reference material for every subsequent flying wing program. The National Air and Space Museum's archives contain thousands of pages of Horton documentation, wind tunnel results, flight test reports, structural analyses, control system studies. Researchers accessing these files consistently express surprise at the sophistication of the brothers' work. Without formal engineering training, without computational tools, without wind tunnel access until late in the war, the Hortons developed understanding that took formal research programs decades to replicate. Dr. Russell Lee, curator of aeronautics at the National Air and Space Museum, supervised the Horton Archives cataloging in 2006. His assessment summarized the brothers' achievement. The Horton documentation represents empirical science at its best. The brothers observed, hypothesized, tested, and refined through hundreds of iterations. They solved problems that theoretical aerodynamics said were unsolvable because they didn't know they were supposed to be impossible. This is exactly how scientific breakthroughs happen, through persistence, observation, and willingness to ignore established dogma. The HO-229V3 prototype, captured in 1945 and shipped to America, spent decades in storage at various military facilities. The aircraft deteriorated, its wooden structure vulnerable to humidity and temperature variations that Wright-Field storage buildings couldn't prevent. By the time preservation became a priority, significant damage had occurred. In 2011, the Smithsonian Institution began restoration of the HO-229 for eventual display at the National Air and Space Museum's Udvar-Hazy Center. The restoration team, examining the aircraft's construction in detail for the first time since capture, discovered evidence supporting the accidental stealth theory. The charcoal-laden plywood skin, originally applied for structural reasons, showed radar-absorbing properties when tested. The swept leading edges, designed for high-speed aerodynamics, deflected radar as effectively as purpose-built stealth features. The restoration project manager, Ken Hyde, described the team's findings. Every time we examine a component of this aircraft, we discover capabilities the designers didn't intend. The stealth characteristics were accidental, a byproduct of construction techniques chosen for entirely different reasons. But the aerodynamic features were deliberate, sophisticated, and correct. The Horton brothers knew exactly what they were building aerodynamically. They just didn't realize they were also building the first stealth fighter. The restored HO-229V3 went on display in 2012, positioned near the B-2 Spirit in the museum's Boeing aviation hangar. The juxtaposition is deliberate. Visitors can see the direct lineage from wartime prototype to modern strategic bomber. Display panels explain the technical connections, the 60-year gap between rejection and acceptance, and the role of captured German technology in shaping American aerospace development. The exhibit attracts aviation enthusiasts, military historians, and aerospace engineers who recognize what casual visitors might miss. The aircraft that looks like a curious Nazi prototype is actually the foundation of modern military aviation. The rejected design became the template. The dangerous configuration became the standard. The impossible became inevitable. The broader lesson extends beyond aviation technology. The Horton story demonstrates how breakthrough innovation often comes from outsiders, unconstrained by established knowledge. The brothers' lack of formal engineering training freed them to pursue solutions that credentialed engineers considered impossible. Their empirical approach, build, test, learn, repeat, produced insights that theoretical analysis couldn't achieve. This pattern repeats throughout technological history. The Wright brothers were bicycle mechanics who solved problems academic aeronauts couldn't. Henry Ford was a farmer's son who revolutionized manufacturing without engineering education. Steve Jobs dropped out of college before transforming multiple industries. Breakthrough innovation often requires the freedom to be wrong that formal education sometimes suppresses. The Horton brothers possessed this freedom. They didn't know their flying wings were impossible, so they built them anyway. They didn't know stability required tail surfaces, so they achieved stability through wing design instead. They didn't know radar would someday determine air combat, so they accidentally created aircraft invisible to it. The final assessment of the Horton legacy belongs to aerospace historian David Myra, who spent 30 years documenting the brothers' work. Walter and Remar Horton represent the most significant unrealized potential in aviation history. They developed technology that could have changed the war's outcome if deployed earlier. They demonstrated concepts that would take 50 years to rediscover. They solved problems through intuition that formal research couldn't crack. Their tragedy wasn't that they were wrong. They were spectacularly right. Their tragedy was being right too early in circumstances that prevented their insights from being recognized and applied. The flying wing works. The stealth characteristics are real. The efficiency advantages are proven. everything the Hortons claimed has been validated by decades of subsequent development. When you look at a B-2 Spirit flying overhead, you're seeing the Horton brothers' vision realized at last. The shape is theirs. The principles are theirs. The future they imagined in a German glider club in 1931 is now the present of military aviation. They were rejected, forgotten, and vindicated in that order. The rejected jet design didn't just accidentally invent the future of flight, it defined it. The HO-29 sits in the Smithsonian today, 78 years after its final flight, surrounded by aircraft it inspired but never influenced directly. The wooden skin is cracked. The jet engines are silent. The cockpit where Heine Dittmar once sat is empty. But the aircraft's legacy flies in every stealth bomber, every advanced drone, every flying wing concept under development worldwide. The future of aviation wears the Horton brothers' fingerprints, even as few remember their names. The rejected design became the foundation. The dangerous concept became the standard. The impossible aircraft became inevitable. In January 1945, German officers rejected the HO-29 as too radical for production. In January 2023, the U.S. Air Force announced the B-21 Raider, the next-generation stealth bomber that will replace the B-2. The B-21's configuration, flying wing, swept leading edges, buried engines. The Horton brothers' vision, rejected 80 decades ago, continues to define the future of flight. The laughter died in 1945 when the war ended and the HO-29 was captured. The mockery faded in 1989 when the B-2 first flew. The dismissal ended in 2012 when the restored HO-29 took its place in the National Air and Space Museum next to the aircraft it inspired. The Horton brothers were right. They were just right too early. And in being right too early, they accidentally invented the future of flight, a future that took 60 years to arrive, but carries their vision into a century they never imagined and a world they helped create. The rejected jet design didn't fail. It waited. And in waiting, it became the backbone of modern aviation, the foundation of stealth technology, and proof that the most important innovations often come from those who don't know what's supposed to be impossible. The Horton brothers built the future in a glider club. The world took 6 decades to catch up, but catch up it did. And now, every time a flying wing crosses the sky, military or civilian, manned or unmanned, visible or invisible, the Horton brothers' rejected design flies again. The future they invented is here. The question is no longer whether their vision was correct. The question is how much further it will take us.